this video, we'd like to discuss finding zeros of a polynomial function. And finding zeros, it's a real simple idea, but not always an easy thing to do depending on the algebra involved. But real simple, a zero of a function is really when your y value or your f of x value is equal to 0. So what we're going to do is we're going to replace the f of x with 0 in this example, and every example, to find zeros. Okay, so this is the problem that we're attempting to solve. Now this is when it can either turn easy or tricky for you. This is a quadratic equation, right? Because you have an x squared in your problem. Now there's a couple of ways to solve quadratic equations. One way is you can attempt to factor the problem, but it doesn't always factor. So with a quadratic equation, you can either try to factor it, or you could use the quadratic formula. On this one, let's just attempt to factor it, and if it factors, we'll go that route. If it doesn't factor, we'll use the quadratic formula. Now, these are a little tricky to factor. Some people can jump immediately into your two sets of parentheses and play around with the numbers until you get this. On the other hand, some folks would prefer to use this little trick where you multiply these two guys together, the leading coefficient, or your x squared coefficient, times your constant, and try to find numbers that multiply to be negative 30 and at the same time add to be 13. And if there are two numbers that do this, that means this problem factors, and we'll attempt to do that. And there are a positive 15 and a negative 2 do both of these things. They multiply to be negative 30 and they add to be positive 13. So that doesn't mean that now you do x plus 15, x minus 2. That's not what's going on here. The next step is you rewrite the middle term. So you have 6x squared comes down plus, now this 13x now is going to turn into 15x minus 2x. Notice that does add to be 13x minus 5. So notice I recopied the exact problem, but I replaced 13x with the two numbers we found, 15x minus 2x. Now I'm going to do factor by grouping. So what factors out of these first two terms is a 3x, and that leaves 2x plus 5. Here, I have to be left with 2x plus 5, so I'm going to pull out a minus 1 times 2x plus 5. And then our next step is to pull out the common 2x plus 5 times 3x minus 1. Now, once your polynomial is factored, you know what to do next. You set each factor, and I'm going to the top of the page, separately equal to 0. Okay, so I'll subtract 5, divide by 2. That gives me x is negative 5 halves. And then I add the 1, divide by 3. That gives me x is 1/3. So this is solving two linear equations, which I know you're familiar with as well. Okay, now let's practice more of these. The more of these you see, the more comfortable you'll feel. There is something I want to point out to you. If you'll notice, this problem is a degree 2. And look how many zeros we have. We have negative 5 halves and 1/3. We have 2 zeros. And you should expect that. The value of your degree and the number of zeros matches. So if you had a degree 5, you would expect 5 zeros. A degree 1, you would expect 1 zero. And that's what you should look for. Next problem, calculate the zeros for this function g of x. Again, the very first step when it says calculate zeros is to set the function equal to 0. So I replace the g of x with 0, and I am just recopying the polynomial. Our next step would be to attempt to factor it. Now, this is a degree 3. So you remember we should expect 3 zeros when we get finished with this problem. Now, degree 3s are often not factorable, at least easy to see how they factor. It's not like you could use the quadratic formula if it doesn't factor either. So you've got to be given a problem at this stage that you can factor, and factor by grouping is the way to go. Anytime you see 4 terms, think, okay, maybe I can do factor by grouping. What comes out of this first set is a 4x squared, and that leaves you with x plus 3. In this term, nothing factors out, but that's okay you're really just pulling out a 1 because you're still left with the common x plus 3. Remember the trick about factor by grouping, what's in the parentheses must match. And you're not finished there either. You got to pull out the matching parentheses, and you have 4x squared plus 1. You would factor more if possible. X plus 3 is linear, so it's x to the first power. It's not going to factor further. 4x squared plus 1 is a square, so it's a possibility that it would factor further. But it's what we call a sum of squares problem, and that does not factor further. So now it's time to set each factor separately equal to 0. Here we subtract the 3 over to get negative 3. That's pretty straightforward. This one is not as obvious. We'll subtract the 1. That gives you 4x squared equals negative 1. Divide by 4. That's x squared equals negative 1/4. Then you must take the square root of both sides. Okay, so using the square root property, plus or minus is involved there. Notice there's a negative under the square root, so that's an imaginary. You pull that out. And then you can also take the square root of 1/4 to get 1/2. It's better written as plus or minus 1/2 I. And notice the number of zeros. We've got 3. We've got negative 3. X is negative 1/2 I. And x is positive 1/2 I. And zeros can be imaginary numbers. They can be real or imaginary. Again, notice the count, too. This is an x to the third problem, and we have 3 zeros. So for our next problem, I'm going to set the entire function equal to 0, because notice it asks us to calculate the zeros. And then it asks for something that we haven't discussed yet, and that is the multiplicity of each zero. Now, when you look at this problem, look, it looks like it might already be factored, but it's not completely factored, and let's do that. Okay, x minus 1 squared. If you like, you can write it as x minus 1 times x minus 1. No need to multiply this out. I know that's your tendency, is you want to start doing the distributive property, but you don't want to do that. It's factored. The x plus 2, I'm just copying. X squared minus 4 is not factored, but can be factored further. It's a difference of squares. The square root of x squared is x, which goes in the first spot of your two factors. The square root of 4 is 2. It goes in the second spot. And you have one factor that's plus and one factor that's minus. And this is completely factored. Now it's time to set each factor equal to 0. Now the question is, can you set 2 equal to 0? Well, you can, but you don't really get a solution. That's impossible. Another way to think about this 2 is you could, in the beginning, divide each side by 2, and it simply disappears because 0 divided by 2 is still 0. Now, if this is a variable, you can't do that. But if you have a constant in the front, you can eliminate it by dividing both sides by that value, or you can just ignore it because it doesn't affect the value of your zeros. So I'm going to set x minus 1 equal to 0, x minus 1 equal to 0, x plus 2 equal to 0, x plus 2 equal to 0, and x minus 2 equal to 0. This gives me x equals 1, x equals 1 again, x equals negative 2, x equals negative 2 again, and x is equal to positive 2. Now notice x equals 1 showed up twice. That means it has what we call a multiplicity of 2. X equals negative 2 also showed up twice. That means it has a multiplicity of 2. Now multiplicity just means how many times that 0 showed up. X equals 2 has a multiplicity, I'm not going to write it all the way out, I'm just going to abbreviate it, of 1. Okay, because it only showed up one time as a 0 of this polynomial. Now, we didn't talk about the degree of this polynomial, but you see that this is x squared. This would be x to the first, and this is another x squared. And remember, when you're multiplying bases, you add exponents, so this would give you an x to the 5th power. So that means we have 5 zeros. And notice we do 1, 2, 3, 4, 5. Even though some of them have a multiplicity of 2, you count them separately as far as the degree goes. Now the multiplicity is significant to the graph, and we'll talk about that soon after we do some more examples. Here we go again. Let's calculate the zeros of the polynomial. Now notice this polynomial is not expanded like the last one. It is not already factored for us. I mean, it is expanded. It is not factored for us, so we need to get this thing factored. I do notice that it's a degree 3, so I'm expecting to have 3 answers. Let's see what we come up with. Notice also this problem is asking us to find the multiplicity of each 0, which is not really asking a whole lot on top. Now, we've got 4 terms. That's telling me I need to do, or at least try, factor by grouping. Now, when I look at my first 2 terms, there's an x squared in common, which means I'm going to be left with 3x minus 5. In my second set, I don't have a 3x minus 5, so I need to pull out something common. It looks like it's a 9, so I'm going to pull out a positive 9. That's going to leave me with 3x minus 5, which is good, because remember, these must match. Then you write down the matching factor, 3x minus 5. You're really factoring it out, times x squared plus 9. You factor further if you can. This is linear. It's not going to factor further. This is a square, but it's a sum of squares. So that won't factor further either. So let's keep going. 3x minus 5. I add the 5, divide by 3, and I get x equals 5/3 is one of my zeros. X squared plus 9 equals 0. I'm going to subtract the 9 and use the square root property. Remember, when you use the square root property, you must put a plus or minus in front of your result. The square root of negative 9, you know, is plus or minus 3i. And how many zeros is that? Well, it's 3, right? It's 1, 2, 3. If we list them separately, 5/3, 3i, and negative 3i. That's 3 separate zeros, and they all, each of them, have a multiplicity of 1. They all showed up just one time each. So now I want to show you how multiplicity affects the graph of a function. So if a 0 has an odd value multiplicity, what that means, if a 0 shows up 1 time or 3 times or 5 times, so the multiplicity is an odd number, then the graph of the function crosses through the x-axis at that point. So let's just say x equals 2 is a 0, and let's say the multiplicity of that 0 is 3. So you would have x equals 2, x equals 2, x equals 2. It shows up 3 times. Then what could happen on the graph is the graph, if it's coming from this side, it would just cross through the x-axis and continue what it's doing. So it's going to cross over the x-axis, just like crossing a lane of traffic, okay? Now, on the other hand, the other option is if a 0 has an even valued multiplicity. What's going to happen is the graph of the function just touches the x-axis and goes the other way. So let's just say x equals 2 is a 0 again, but the multiplicity this time is 2. So x equals 2 shows up twice, okay? So here's x equals 2 on the graph, and notice that last one I did, I plotted it at x equals 3, but I meant that to be x equals 2, so what I'm going to do is I'm attempting to fix that. There we go. Now it's at x equals 2. Okay, so for our next example, again, I'm attempting to graph at x equals 2, but this time the multiplicity is even. So let's just say the graph started on this side. The graph would touch and go back the other way. So it doesn't cross over the axis, it simply touches and goes back the other way. So all of this information that we've learned so far about end behavior, which is the leading coefficients test, and zeros has to do with graphing the function. So in the next problem, we would like to graph a function using all that information. So the steps to graphing, we want to determine the end behavior, which is using the leading coefficient test. Then we want to calculate the zeros, like we've done in this video. We want to list the x-intercepts. Those are actually the real valued zeros. I know you probably noticed this, but zeros and x-intercepts are the same calculation. You're doing exactly the same thing, except x-intercepts can't be imaginary numbers, but zeros can. Okay, then you want to determine the multiplicity of each 0, because we know if it has odd multiplicity, it crosses over the x-axis. If it has even multiplicity, it touches the x-axis and goes back the other way. We want to calculate the y-intercept. You know, that's always easier than calculating an x-intercept. You want to determine if the function has symmetry. This is optional. I can discuss this, but you can get a good looking graph without discussing symmetry. And then you definitely want a very important plot extra points. It's very important to plot extra points, and we're going to do this between and beyond every x-intercept. So let's try one problem before the end of the video, and then we'll do another video where we do some more examples. So step 1, we want to talk about end behavior for this problem. Okay, we're going to use the leading coefficient test, and that says you need to know the degree, and the degree is 3, which is odd, and the leading coefficient is 1, which is positive. Now remember, if you're dealing with odd, you know that the left and the right side are doing two different things, because odd means opposite in this case. So the left side is pointing downward and the right side is pointing upward, because you're talking about a positive leading coefficient. The next thing we're going to do is calculate zeros. Okay, so set the whole function equal to 0. Now when you factor, the very first thing you should do is look for a greatest common factor, and this problem has that. So I'll pull out the x. That leaves me with x squared minus x minus 6. And now I factor x squared minus x minus 6. That's a basic trinomial. We're trying to find numbers that multiply to be -6 and add to be -1. And you know those are -3 and +2. And then I set each one of these factors separately equal to 0. Even the x, because the x is a factor with a variable. So you have x equals 0, x equals 3, and x equals -2. Now remember, the next step after that, we can go back and take a look at the steps. So we did the leading coefficient test. We determined the zeros. Left was down and right was up. Next, we're calculating the zeros, so we have that. We're supposed to list the x-intercepts. Those are the real valued zeros. And note whether the graph touches or crosses over the x-axis. Okay, so these are all real valued answers. So one of our x-intercepts is 0, 0. Another is 3, 0. And another is -2, 0. All of these also have a multiplicity of 1. That just shows up once. That shows up once, and the multiplicity there is 1. So all of these cross over the x-axis at that value. Okay, now the next thing we need to find, and I'm going to continue this in a different color, is the y-intercept. So to find a y-intercept, you set x equal to 0. Rather than f of x or y equal to 0, you do the opposite and set x equal to 0. So I'm going to have y equals 0 to the third minus 0 squared minus 6 times 0, which just gives you 0. So our y-intercept is the point 0, 0. Okay, now let's go back and look at our list. The next thing is optional. You want to talk about symmetry. Now I'm going to show you that very quickly just so you know what that is in case you're ever asked to do that. But for me, it's always an optional step. Okay, so symmetry. To calculate symmetry, you've done this before. You substitute -x in everywhere there's an x. So -x to the third minus -x squared minus 6 times -x. If when you simplify this expression, so negative to the third is -x to the third, -x squared turns positive, but this negative remains, okay, and then -x times the -6 is plus 6x. If you get exactly the same thing as your original function, then it's even. And we don't have that. Our signs, some of them have changed. If you get the opposite, so it's not the same, it's also not opposite. Okay, so the same would be even, opposite would be odd, and this is neither. And that's one reason I don't like to calculate symmetry, is because often you get neither for your polynomial, and that will help you graph it. Okay, so maybe we'll run into one that does have symmetry, or maybe I won't do it because, again, it's optional. All right, and then the next step is plot extra points. Okay, so let's take all this information to another page. So we have 0, 0, 3, 0, negative 2, 0. So we want to plot those points. And this was also the y-intercept. Now notice I didn't put a scale on here because the y-scale, we just don't know what we're going to be dealing with. So let's do an x scale for now. So I'm going to 5 in each direction. And we plot our points, so I've got 0, 0, 3, 0, and negative 2, 0. Now the rule is, if I go back to our rules, the rule highlighted here, plot extra points by completing a t-table using points between and beyond every x-intercept. So when I do a t-table, I want to make sure I go between these x-intercepts and beyond. So starting on the left over here, I've got negative 2. I need something to the left of negative 2, like maybe negative 3. And something between negative 2 and 0, like negative 1. Something between 0 and 3, like 1 or 2, or both. And something on the other side of 3, like 4. And I'm going to plug these values into my function. So I'm going to calculate f of negative 3 up at the top of the page. That's negative 3 to the third, minus negative 3 squared, minus 6 times negative 3. Negative 3 to the third is negative 27. Negative 3 squared is 9. That's negative 9. And then negative 6 times negative 3 is plus 18. Negative 27 minus 9 is negative 36. And then you do negative 36 plus 18. It's going to give you negative 18. Okay? Now let's do this with negative 1. So I have f of negative 1 is negative 1 to the third minus negative 1 squared minus 6 times negative 1. Negative 1 to the third is negative 1. Negative 1 squared is 1, times negative 1 is negative 1. Negative 6 times negative 1 is plus 6. And this is going to give me 4. Now I plug in 1. So I have f of 1 is 1 to the third minus 1 squared minus 6 times 1, which is 1 minus 1 minus 6. So that gives me negative 6. And then finally, let's plug in 4. So f of 4, I have 4 to the third minus 4 squared minus 6 times 4. So that's going to give me 4 times 4 is 16 times 4 more is 64 minus 16 minus 24. That gives me 24. So what we want to do now is plot these points. Now, I don't have a y-scale, and I don't do a y-scale until I know what my y values are going to be. And so notice we've got 24 and negative 18. So maybe on this short y-scale here, if I scaled it off as, say, 5, 10, 15, 20, 25. Okay, so 5, 10, 15. You've got to let somebody know what that is. So negative 5, negative 10, negative 15, negative 20. And then, of course, negative 25 would be right here. Now, let's plot these points. So, negative 3, negative 18. So, almost down here at negative 20. Negative 1 is 4. Remember, that's 5. So, I'm going almost up to 5. 1, negative 6. So, that's negative 5. The negative 6 would be just a little lower. And then 4, 24. Up here right in the middle of my 16. Then you connect your dots from left to right. Now this implies that it goes up forever to the right and down forever to the left. We need to check and make sure that's what we stated would happen. If we go back and look at our previous page, notice we said the left would be down and the right would be up. Is that what we have? Yes, the left is down, the right is up. What about our zeros? Remember, the multiplicity for each of our 3 zeros was 1, which means it's supposed to cross over, cross over, cross over, and notice it does. It crosses over each of those zeros. So all this information matches up with what we got as our calculations on the previous page. So I hope you'll come back for another video where we're going to do just several more of these problems and practice these techniques of finding zeros in behavior, y-intercept, and plotting extra points.